Here are solutions for the spring 2016 final exam for Math 213. The first problem on their final exam, which will be the first problem that you will see on the 2017 winter 17 final exam, will be something off the midterm. So I'm going to work on this problem, although this might not be the same even concepts that you will be covering on your first problem. Rather than spend too much time on this problem, my advice to you is to go back and look at your midterm and make sure you can redo any of those midterm problems. But there's enough relevant ideas in this problem that I'm going to go ahead and do it anyways. So really, this is a topic from their midterm. What's going on in this first one is we have a semi-regular 4-6x tessellation. So I don't know what x is, but I have to figure out what x must be in order to make the measure of the internal angles all work out. So what I need to recognize is that if I have a tessellation, that the sum of the internal angles of the polygons that meet at that vertex have to be 360 degrees. So I can figure out what x is kind of the remainder. This 4 right here has an internal angle of 90 degrees. And I think that that's pretty obvious. A 4-sided regular polygon is a square, and the internal angle on a square is 90 degrees because we get right angles at each vertex. For a 6, it's a little bit trickier. So for a 6, maybe I'll do that down here. For a 6, it kind of helps to think about the fact that if I had a 6-sided polygon, so I don't know, it looks something like this. What would this angle be equal to right here? I guess I could draw the whole polygon if I really wanted to. I don't know if I really want to, but I've gone this far. 1, 2, 3, 4, 5, 6. There's a poorly drawn 6-sided regular polygon. I want to figure out the measure of an internal angle. Well, I could figure out the measure of this central angle right here because I know it must be 360 degrees all the way around, and I could draw 6 triangles here that would all be congruent. So the measure of this angle right here must be 1/6 of 360. In other words, exactly 60 degrees. And if this is 60 degrees, then because this is an isosceles triangle, these two angles are congruent. So I have 180 minus 60, in other words, 120 left over for these two. But since they're the same angle, these must be 60s as well. Not always the same as this, but these two always have to be the same. And if I know these two and I recognize that 2 of these guys make up 1 of these, I get that this angle right here must be 120 degrees. So my interior angles, I get 90 plus 120. And if I sum those, I get 210. So what's left over is 360 minus this 210. In other words, what I have left over is 150 degrees. So what I have to figure, I guess just ask what must the measure of the internal angle of x be? Well, it must be 150 degrees. So that'd be the answer right there. B says, okay, show how you can use your answer to part A to determine the central angle of x. In other words, do this same argument again, but kind of backwards. And then once you figure out the central angle, figure out how many sides x has. Well, okay, so here's that same argument. I have this shape. I don't know how many sides it has, so I'll just draw this kind of arbitrarily. But what I do know is that the measure of an internal angle here is 150 degrees. So this entire angle is 150 degrees, and so half of it is over on this side. Half of 150 means 75 degrees is over on this side, and another 75 degrees is over on this side. And because I know that the sum of the internal angles in any triangle is 180 degrees, well, if I used up 150 down here, I would have 30 left over up here. So my answer would be 30 degrees. And if I know this angle is 30 degrees, I can think about how many of these angles I could draw to fit with 360 degrees. I could take this 360 and divide it by 30, and I'll get 12. And that's the number of sides of x. So x is 30, and the number of sides for this polygon x must be equal to 12. And so that answers part B. Part C says sketch this tessellation. Make sure to include enough. So the tessellation we just figured out at 12 is what x is equal to. So it's 4, 6, 12. And make sure to include enough to show the naming convention for at least 3 different vertices. So the way I like to do these is start out with the 4, my square, and then pick a vertex. Attached to this vertex, there must be a 6-sided polygon and a 12-sided polygon. Well, of those two, a 6-sided polygon is easier to draw. And these don't have to be perfect by any means, but there's my 6-sided polygon. That means there's a 12-sided polygon right here. But then if I focus on this vertex, I already have the 12-sided and the 4-sided. That means there must be another 6-sided polygon down here. And it should be the same size as the one I drew above, but I'm not a very good artist, especially not on a computer. Maybe if I label some vertices, it's easier to see. So if I drew a 12-sided polygon right here, then I would have this vertex would be surrounded by 4, 6, and 12, and this vertex would be surrounded by 4, 6, and 12. Drawing a 12 is a little bit hard, but the way you can think about it is 12 divided by 4 is 3. So I have these 3 kind of going around each of the 4 sides. So I need 3 more up here. So I don't know, maybe I can draw it. Well, let's cheat a little bit. If I think about this vertex, it's already touching this 12. There's a 12 over here. It's already touching this 6, so there must be a 4 over here. And then I got this 12. 1, 2, 3, 4, 5. And there must be a 6 up here, although I don't need to draw it. And therefore, there must be a 4 down here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So close enough, there's a 12. Now I can pick on this vertex here has a 4, 6, 12 around it. This vertex here has a 4, 6, 12 around it. And this vertex here has a 4, 6, 12 around it. So I could do something like this and call this good enough.